Okay, in this lecture I want to talk about the topics of the projects so that you can see what you want to choose. So I'll go through this list and maybe make some notes. So I added two new papers, the ones that are labeled new. Okay, so let's talk about the first one. So it's called Combinatorics of Tensor Product Multiplicities by Pamela Harris and Jeff Williambring. So in the next chapter, when we talk about symmetric functions, one of the applications is we're going to get a combinatorial rule for the multiplicities of taking the tensor product of two spec modules. And these multiplicities are called Littlewood-Richardson coefficients. And in general, they are hard to compute. So this paper is about one of the results it has a beautiful identity for the sums of squares of these multiplicities. So let me give an example of what the identity. Let me tell you what the identity is about. Okay, so let me write here. Okay, so we have seen, for example, the following identity. If we sum the sum of the degrees of the spec modules for over all the partitions, all the conjugacy classes, we get the size of the group n factorial. So that's a very nice identity. We're going to study it further. Just as an analogy, let me define C lambda mu nu to be the multiplicity of S lambda in the tensor product of S mu with S nu. Okay, so this is a negative integer because it's a multiplicity, but there actually is a combinatorial rule to compute these coefficients. So these coefficients are called the Littlewood-Richardson coefficients. And there's several different objects they count. One is tableau, but they actually have these puzzles that you see on our website. They're called Knudsen-Tau puzzles, for example. Anyways, so these multiplicities are hard to compute, but if you take the sum of the squares, where you sum over all lambda mu nu, where lambda is a partition of n, you get the number of integer partitions of n, where you color the parts black and white. Okay, so that's one of the main results on that first project. So each part we color either black or white. Okay. I mean, it has very interesting consequences for how big these Littlewood-Richardson coefficients are. Okay. So each part has two colors. Okay. For example, here in this case, blue and white. Okay, so that's the first paper. The second one is about a symmetric function approach to the Okounkov-Olshansky way of studying representation theory of the symmetric group. So this is by Sylvie Courtel, Alain Goupil, and Gilles Schaeffer, and the title is called Content Evaluations in a Class of Symmetric Functions. So here is the link. It's a good way of so we're going to see next that we can use symmetric functions to model many of the things we've done in representation theory, and this is doing something similar for this approach of Okounkov-Olshansky that we will see towards the end of the course. Okay, so that's the second one. So the third one is about representation theory of the group of invertible matrices over a finite field. So say n by n matrices over a finite field. This is in some sense, a analog of the symmetric group. So this paper of Green studies the characters of this group. And if you look at the website now, it has a link. And you can also see section 3 of this recent paper by Joe Lewis, Vic Reiner, and Dennis Stanton, where many of these results are summarized. So this is reflection factorizations of a Singer cycle. Okay, and that gets us to the fourth project, Moynihan's theorem and fake degree polynomials. So let me explain what those are. Okay, so let me just tell you what these fake degrees are. Okay, so let me try to put both things at the same time. So, all right. So we have seen that. So what is Monian's theorem about? So remember that we showed that the dimension of the spec module is the number of standard Young tableau of shape lambda. So you can study a refinement of this result where you sum over the standard tableau of shape lambda, and you put certain statistic called the major index, but it's called stat now. So this is a refinement of the dimension of the degree of the spec module. And if you look at the coefficients of this polynomial, which are non-negative integers by construction, these are called fake degrees, and this is a term given by George Lustig, who's a mathematician at MIT. And these coefficients have a significance. So this paper by Richard Stanley has so it's related to this result. Okay, so fake degree again is the ith coefficient of this polynomial. Okay, so the next project I want to discuss is multiplicities of tensor product representations. So for example, if you take the product of the two characters chi mu chi nu, this is a class function where mu and nu are of partitions of the same size. So because of this, we can write them in terms of characters, since characters are a basis for class functions. So we can write it as a linear combination of the characters chi lambda, and we have these coefficients g lambda mu nu. So these happen to be also non-negative integers, and this can also be understood from representation theory. However, we don't have a combinatorial rule, so kind of different to the story about little Richardson coefficients. We don't have a rule about these coefficients. That's a big open problem in algebraic combinatorics. So this paper by Ernesto Vallejo studies some stability property of these coefficients that was first discovered by Murnaghan. Okay, so the next paper is with an application of representation theory, a recent application. So this is a paper by Igor Pak and Greta Panova about strict unimodality of Q binomial coefficients. So it's a short paper, but if this one is chosen, I'll give you some other readings. So recall that the binomial coefficients are in choose K, count the number of K subsets of 1 up to n. There's a Q analog of the binomial coefficient, which we denote with these like square braces. So to define it, let me define some things. So we have the number n, and the Q analog of the number n is just the polynomial 1 plus Q plus dot 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 Q to the n minus 1. So if you plug in Q equals 1, you recover n. And then I can define an analog of n factorial, which is just multiplying these numbers. And then the Q binomial coefficient, I could define it as just the ratio of these Q factorials. So just as binomial coefficients are a ratio of factorials and it happens to be an integer, they count something, a Q binomial coefficient, this kind of ratio of polynomials, happens to also be a polynomial. And moreover, a polynomial with non-negative coefficients. So these are very interesting polynomials, and then maybe a question dating back to Sylvester is looking at the unimodality of the coefficients of this polynomial. So these coefficients, the coefficients of this n choose K as a polynomial in Q, kind of they increase, and they weakly increase, and they decrease, and this paper by Igor Pak and Greta Panova establishes actually strict unimodality. So of this coefficient, so they actually keep increasing strictly until they reach a plateau, and then they decrease strictly. And the proof uses representation theory. Okay, so the next set of papers is about the matrix of the irreducible characters. So the first paper by Alex Miller looked at the sparseness of this matrix, so the probability that a character value is 0 in the symmetric group. And the second result looks at the congruences of this matrix too, of this character table. Okay, so the next project is about counting factorizations of permutations using characters. So in a homework we saw how we can use characters to compute the number of factorizations of an element of a group if we want to control the conjugacy classes. So say that in a symmetric group I want to write the long cycle size n as a product of n minus 1 transpositions. Okay, so for example, if I have the long cycle 1, 2, 3, I can write it as first 1, 2, 2, 3 when I'm multiplying from right to left, or I could write it as 1, 3, 1, 2, or I can write it as, let's see, I can do 2 goes to 3 and, sorry, okay, 2 goes to 3, I guess 2 goes to 3 and 1 goes to 3. So there's only these three ways, and in general, the number of such factorizations is n to the n minus 2, which is the number of spanning trees with a number of vertices, or actually it's the number of trees with vertices 1 up to n. Okay, and there's a really nice bijection explaining that. So you can also arrive to this result using characters. So this is what this paper of David Jackson is about. Okay, so then we get to standard tableau and characters. This is a paper by Jean Douce and Valentin Ferré. There's a typo here in the last name of Jean. I'll fix that. So we've seen standard tableau, for example, of shapes lambda, because they give you as the basis of the spec modules. But there's a generalization to something called skew shapes. So let me explain what this generalization is. So let me go here, okay. All right, so remember that f lambda is the number of standard Young tableau of the shape lambda, which is a dimension of the spec module. And this has a beautiful formula that we're going to see in the next chapter called the hook length formula. So you can write it as n factorial divided by the product of certain numbers called hooks. So we're going to study this formula in detail. Okay, so this is really one of the highlights of the course. So we will, and there's more projects about this we'll see later. So okay, so here's kind of what a standard tableau looks like of shape lambda. So a generalization of this is to look at skew shapes. So standard tableau of skew shapes. So we have a shape lambda and we kind of bite off a shape mu out of it. Okay, so we call this a skew shape, and we can again look at a standard tableau, so a tableau where the rows and columns are increasing, and if we have n cells, we use the numbers 1 up to n. Okay, and so then the number of of standard tableau of skew shapes have no product formula. So they don't have a product formula as pretty as the case of the shape lambda. So we call these formulas hook length formulas. So skew shapes, the number of standard tableau skew shapes don't appear to have a hook formula. However, they have a determinant formula, so it's not so bad. But then they're harder kind of to compute. So this paper uses characters to study bounds on the number of standard tableau. Okay, so the next couple of projects are about this hook length formula for the number of standard tableau of shape lambda. So the first one is a probabilistic proof of this, and this is by Curtis Green, Nijenhuis, and Wilf. So I have to update the authors here. And there's also an exercise in Sagan's book in chapter 3. So that's what this first paper is about. Okay, so it's really about giving a probabilistic proof of this formula. Okay, so it's quite pretty. And the next project is about a bijective proof of this formula. So this bijective proof it's quite symmetric. The probabilistic proof was in 1979. The bijective proof came in 1997, and it was by Novelli, Pak, and Stoyanovsky. And there's also a section in chapter 3 in Sagan's book about this. So this can also be a reference for that project. So again, there's two projects about this hook length formula: the probabilistic and the bijective proof. the next project is about there's two projects about the chromatic symmetric function. So this symmetric function was defined by Richard Stanley, and it generalizes the chromatic polynomial of a graph. So the first paper is the original paper when they were defined. The second one is chromatic symmetric functions and representation theory. So John Sharashian and Michel Wax found this generalization of this chromatic symmetric function, which is called a chromatic quasi-symmetric function, and they found a very interesting link to representation theory and some very nice work by Juliana Timochko, who is at Smith. So there's some references in this paper about this work, and this is an area of very active research right now. So then we get to this next project about factorial Schur functions. So this is a generalization of Schur functions. So we'll talk about Schur functions in the coming weeks, but let me explain more or less what are factorial Schur functions. Okay, so a very important basis, or the most important basis of symmetric functions, are Schur functions. So they're indexed S lambda with the lambda underneath. So they have several definitions. We'll study them. One of them is as the ratio of two determinants. So on the bottom we have the van der Monde determinant in several variables. Okay. And in the numerator, we have like a variant of the van der Monde. So the details here are not so important, but you have here a matrix of monomials in the variables xi. So this is called the bi-alternant formula. Okay, so a factorial Schur function, they were defined by MacDonald, is, well, what if you take this matrix of monomials and you replace each monomial by a factorial, a falling factorial. So you might know that, so we know that the x to the n is a basis for polynomials, but another basis for polynomials are falling factorials. So things like x times x minus 1 times x minus 2 ... x minus k plus 1. So a factorial Schur function is when we replace this numerator here by a factorial. Okay, so here is what I was just saying about the basis of polynomials. And so yeah, so falling factorials are also a basis of polynomials. So what happens if we replace the numerator by a factorial? And that's more or less what factorial Schur functions are. They're very interesting. So this paper by Moldev and Sagan studies these functions. Okay, and last but not least, there is this project on the Jacobi-Trudi identity. So it's another identity of Schur functions. So this is a paper by Stanley and Stembridge. So let me explain a little bit what this is about. So another way to define Schur functions is as a determinant of another basis of symmetric functions. So this is called the Jacobi-Trudi identity. So we can write as a determinant of these functions h, which are called the complete symmetric functions. Okay, so we will study all this in the coming weeks. Okay, so yeah, so that's what the Jacobi-Trudi identity is. Now, and actually from so what are immanents from this Jacobi-Trudi identity, we can get actually another formula. Well, so recall that the number of standard tuples. So we're going to see why this is the case. So not only do we have the Hooke length formula, but you also have a determinant formula that is more or less like this. I'm missing multiplying by an n factorial if lambda is a partition of n. So there's a typo here. Okay, but anyway, so what are immanents, which is the other keyword on this title? Well, recall that we can write a determinant as a sum, as an alternating sum over permutations. So if we have a determinant of a matrix of size n, we can write it, or of size m, sorry, we can write it as a sum over all permutations of size m. We have the sign of the permutation, and we have a1 w1 dot am wm. Okay, so that's the kind of the one definition of the determinant. You know what happens if we replace the sign of the permutation by 1? Okay, so here this sum is no longer alternating. So do you know how this is called? So this is called actually the permanent of a matrix. And in general, they're quite hard to compute because in some sense there's no cancellation to help us out. You know, with a determinant, I mean, if you use the sum over alternating sum over permutations, it's a very big sum. It has m factorial terms, but thankfully we have things like row reduction that allow us to compute a permutation, a determinant in a fast way. So you know, when you do row reduction, roughly, you can compute the determinant if in m cubed operations. So much better than this alternating sum. But you don't have these tricks for the permanent, so this is actually hard to compute. But it is of interest because sometimes it can help you count perfect matchings of a graph, and there's other applications. Okay, so that's the determinant, that's the permanent. What's an immanent? So, well, we can view this the sign in the first sum of the determinant as the value of the sign representation, and we can view the 1 in the permanent as the trivial character, right? So the value of the trivial representation. So what if we replace that by the character of a fixed, so the value of a character chi lambda at w. Okay, so why not? So this is what an immanent is called. Okay, and so the immanent depends on lambda, the irreducible character of the symmetric group we chose. Okay, and these sounds like a crazy definition, but it actually has a significance in representation theory. So and in combinatorics. So this is what this paper is about, and it has some results also on the forgotten symmetric functions. So I think I mentioned this basis on the very first week of the class when we were giving an overview of the topics. Okay, so here's a list of projects. So so please take your time and choose the topics and let me know what you choose.